Hey everyone, here's our notes for 1.6 latent heat. So latent heat has to do with as we keep adding heat to a substance, what happens to its temperature? So as I keep adding heat, will its temperature continually rise and at a constant rate? Or what will happen? So a quick answer is no, it will not continue to rise at a constant rate. This would be an example of a graph of the melting of ice. Okay, so and we can see that it does not just keep going. So there is this flat bit here. So the flat part shows a change in state. So all the energy, all the heat energy, remember heat is energy, joules, is being used to melt the ice, not raise the temperature of the substance. So all the energy, all the heat getting put in is for melting the ice instead of changing the temperature here. So at this flat bit, we have our ice melting into liquid water. If we zoom out and take a look at this whole graph, let's say we continue melting that ice and turn it into steam, this is what that graph would look like. So here we would have our ice, here we would have our liquid water, and here we would have our steam. So taking a look, what temperature would this be and would this be? Well, for water, when do we melt? Okay, so remember this line is where we have water melting, and this line is where we would have water so turning into steam, so boiling. Okay, so melting and boiling, well, I melt at 0 degrees Celsius and I boil at 100 degrees Celsius for water at sea level. Okay, so we can also go down, so I can also turn steam down into ice, and it's going to follow the same curve. So when I'm turning steam into ice, this would not be considered, it's still the boiling point, but I would be condensing. So steam condensing into water or water freezing into ice. Okay, so anything under here will be ice lower than 0 degrees Celsius, right at this line is a mixture of ice and water as it's turning into water if it's melting at 0 degrees Celsius. So ice at 0 degrees Celsius and water at 0 degrees Celsius. And all along here you have water all the way from 0 to 100 degrees Celsius. At 100 degrees Celsius, if you keep adding heat, you're going to start getting steam, or if you take away heat, you're going to start getting water. Okay, and up here we have water as steam that's over 100 degrees Celsius. So what's happening? Now, latent heat occurs when there is a state change. So although heat is lost or gained, so I am gaining heat or losing heat, the temperature does not change. Okay, so that's why it is flat. So here's our boiling point, our melting point. Okay, solid, liquid, gas, we already talked about that with water on our previous slide, and here we would have a liquid gas mixture, here we would have a solid liquid mixture. Now what is actually happening where the heat is going? So anytime I have heat gained during latent heat, so during those phase changes, it goes into breaking the bonds between molecules. So if I am increasing heat, so I'm turning a solid into a liquid, what is happening? There are bonds between the molecules in a solid. Okay, when we are turning our solid to a liquid, what ends up happening is all the energy, all the heat energy goes into breaking those bonds that are there. Okay, so we're breaking the bonds between the molecules, and that is where the heat is going. Breaking those bonds. Okay, and then turning it into liquid. So they're not bonded together anymore. They're free to move around. Okay, same thing if I'm turning from liquid to gas. So there is still bonds between them. They're not as strong bonds as they are with solids because they have more freedom of movement with liquids, but there are still bonds. So in turning to a gas, those bonds need to be broken again, and that's where that heat energy is going to. Same thing, but opposite. if heat is being lost. So if heat is being lost, so going this way, going from, for example, a gas to a liquid, losing heat, so the gas gets colder, all the energy that is getting lost is actually going into forming those bonds instead of losing temperature. Okay, so there were no bonds, and now those bonds are getting formed. Okay, so as we go here, all that energy goes into forming bonds. So the energy that looks like it's getting lost is actually going into the formation of bonds. If I'm rising in temperature, the heat that's going in, that's not raising the temperature, is breaking the bonds. Okay. So in general, here's our heat staircase. And anytime we're changing states, I am going to require you to draw this. So in general, oops, use different color. Go. And here we go. So at this point, it's 100 degrees Celsius for when we're talking about water, because that's water's boiling point. Okay, so right here is our boiling point, but that's going to change for different substances. Not all substances obviously boil at 100. So our boiling or condensing point. So temperature. Right here is our melting or freezing temperature. Okay. So if we follow the staircase up, go up the stairs, during this portion, we are a solid. This portion, we are a liquid. And this portion, we are a gas. Right here, we're a mixture of liquid and gas. Right here, we're a mixture of solid and liquid. Okay, at the same temperature. So for water, this would be, if you were in this region, you would have some solid ice and you would have some liquid water, but both at 0 degrees Celsius. Of course, that will change for different substances. Okay. There are formulas that we are going to need to use. So we're going to come back to this slide after talking about what our formulas for latent heat are. Now, we can't use our Q equals mc delta T because it has a change in temperature. And with latent heat, there is no temperature change. So the temperature is not rising, it's not falling. So I can't use Q equals mc delta T. So over here, where I do have my temperature rising or falling, depending on which way you're going up or down the staircase, I can. So I would use Q equals mc delta T to figure out, for example, how much heat is gained or lost in this region. Same thing here. So Q equals mc delta T. There is a change in temperature, so I can use this formula, and same here. So Q equals mc delta T. So as long as I know the mass, the specific heat of the substance, and the change in temperature, I'm fine. I can figure this out. But here, there is no change in temperature. So this would just be Q equals 0, but we know that heat is still being added. So our two formulas, which are basically the same formula, but with slightly different variables, are Q equals MHF and Q equals MHV. So similar to our specific heat in that you have a mass, but there is no temperature change because latent heat, no temperature change. And instead of C's, we have two different constants. Okay, so where? So Q, as usual, is our heat, measured in joules. Okay, M is the same, it's our mass, measured in kilograms. Now HF and HV. So the F stands for fusion, and the H stands for heat. So this is the heat of fusion, and this is the heat of, and now the V stands for vaporization. So both of these each of these, sorry, corresponds to one of our flat portions on our graph. Now, heat of fusion, think solids. So HFs will be here, HVs, vaporization, that's kind of like steam, will be up here, right? Now, their units, instead of with our C values, our specific heat values, how it was how many joules you need to add to change 1 kilogram of substance per degree Celsius. There is no degree Celsius because we're not actually changing temperature, so it's just joules per kilogram. You need this many joules per kilogram to change this many joules to change 1 kilogram of the substance from a solid to a liquid, or a liquid to a solid, or a gas to a liquid, or liquid to gas. Okay, so to change state. So this many joules to change 1 kilogram of substance into a different state. So these were our specific heats. Here's our heat of fusion and vaporization. And you'll notice that here's specific heat, joules per kilogram degree Celsius or degree Kelvin, and our joules per kilogram, that these are much, much higher. So our heats of vaporization and heats of fusion are higher by orders of magnitude, okay, by like 100 times or 1,000 times higher than our specific heats. What that means is it takes a lot of energy to turn either a liquid to a solid, so to form those bonds, or to turn a solid to a liquid to break those bonds. So that bond breaking and forming takes a lot of energy. So state changes take a lot more energy than just changing the temperature of a substance. Okay, so here's HFs and here's a bunch of HVs. Okay, so sneaking back over here, heat of fusion, we're just going to leave a note for ourselves. So fusion is when we are melting or freezing something. And vaporization is when we are vaporizing, so, or condensing. Okay, so sneaking back over here. So anytime I have temperature changes, I can use my Q equals obviously delta T. That's what I need to use because there's a change in temperature. But anytime I have a state change, I need to use Q equals MHF or Q equals MHV. So these are the formulas that I will use. Okay, so why I'm going to start making you, as we do examples, do the staircase, is to see where you're starting, where you're ending, and see if there are any state changes. So it's going to be really important that you get those state changes in there. Also, if we look at the specific heat capacity table again, so here we have solids, so ice, water is ice. Here we have water as liquid, water as a gas. If you look at your tables, ice, the specific heat capacity of ice is 2060, the specific heat capacity of steam is 2020, and the specific heat capacity of water is 4180. So there are 3 different values for C when we're dealing with water. So it's going to be different C values. So you can't just take water at like -6 degrees Celsius, go up to water at 102 degrees Celsius and use the C of 4180 for all of it, because water will have a different C value when it's solid and it will have a different C value when it's a gas. Okay, well, sneaking on, let's do an example. So how much heat is needed to melt 1 kilogram of lead that's currently at 23 degrees Celsius? Lead melts at 327.5 degrees Celsius. So our first step, anytime we see like melting or boiling or anything like that, it's going to give you a hint that you're going to need to draw your staircase. Okay, so I will require that you draw your staircase. So first step, drawing our staircase and doing our givens. And I'm going to do my givens right on my staircase. Okay, So I'm making this really big for right now. Once you start doing this, you can just do it in the margin of your page and you're probably okay. So how much heat is needed to melt 1 kilogram of lead? Okay, so that mass is going to be 1 kilogram. That's currently at 23 degrees Celsius, and lead melts at 327.5 degrees Celsius. So lead at 23 degrees Celsius at around room temperature is going to be a solid. Okay, so we're just going to put a mark here. Here's our solid lead at 23 degrees Celsius. So remember, solid, liquid, gas. So solid lead at 23 degrees Celsius. Now lead melts at 327.5 degrees Celsius. So this point right here is 327.5. Okay, and we want to melt this lead. So if I go, now we're going to see how far up our staircase we need to go. So starting here, if I go here, I now have solid lead, because I'm still on the solid line, at 327.5 degrees Celsius. It is not yet melted. Just because it's at its melting point doesn't mean it has yet melted. So we need to melt that lead. So we need to get it to liquid lead. Okay, so this will be where we are breaking the bonds between the solid lead to make it liquid. And right here, we have liquid lead at 327.5 degrees Celsius. I could keep adding heat and melting it more, but I don't have to. I just need some liquid lead. This is where it will happen. So this is a 1-2 step question. And that's how you'll figure out how many steps that you're going to have. So 1-2 steps for this one. If I went all the way up to creating gaseous lead, which would be horrible, it would be a 1-2-3-4-5 or 4-step question. So a 4 or 5-step question to get all the way to gaseous lead, which we would never want to do. That would be horrible to breathe in. Okay, so now that we've figured out how many steps, okay, so we calculated the number of steps using our staircase. We can start writing down our formula. So just as usual. Okay, so we choose our formulas and we will solve. And once we solve for them, I am going to have a 5th step. So writing our formulas for each step. Okay, so we have step number 1 and step number 2. So in step number 1, we have a temperature change. So if I was unsure, I could go back to this right here where I have all my formulas written, which one I'm using. If I'm going from here to here, I'm going to be using Q equals mc delta T. I would be able to know that already because temperature change, I will be using Q equals mc delta T. So I'm looking for Q, so I'm looking for how much heat is needed. And I'm given my mass, it's 1 kilogram. I can calculate my change in temperature from here, and I just need my C value. As soon as you see that, oh, it's not in my question, that's right, I can just look over here. So my C value for lead is 130 joules per kilogram degrees Celsius. So my C for lead equals 130 joules per kilogram degree Celsius. Now my delta T, my change in temperature, is going to be my final temperature minus my initial temperature. So my final temperature, I'm getting it up to 327.5 in this step. So taking a look, I'm going from 23 degrees Celsius to 327.5. So my change in temperature will be 327.5 minus 23. And when you calculate that, you get 304.5 degrees Celsius. Okay, so now I have everything I need. I have my mass, I have my C, I have my delta T. So substituting in and solving. So M is 1 kilogram. My C value is 130 joules per kilogram degree Celsius, and my delta T is 304.5 degrees Celsius. So checking those units, I got kilograms with kilograms, okay, good, and degree Celsius on the bottom and a degree Celsius on the top, and I'm left with joules, which is what I want, so I probably put that in correctly. And once again, we're back to you need to have your mass units in kilograms. So if you're given a grams, turn it into kilograms first. Okay, and doing our calculation. So 130 times 304.5, we get 39,585 joules. So we're going to keep that answer. And sneaking on to number 2, our second step. So we're not changing in temperature, so I can't use Q equals mc delta T because there is no delta T. Delta T is 0, which will make everything 0, but that's not what is actually happening. I'm still adding heat. And the heat is going into breaking the bonds between those lead particles. So here I will need a heat of fusion. So Q equals MHF. If I was unsure, I could go back to my notes, take a check. Oh, right, this is MHF is what I'm using here. I'm doing this one and this one. Q equals MC delta T first, Q equals MHF second. And I have my mass, it's 1 kilogram. I just need to look up my HF now. So over here, go to your common constants, and for lead. So I'm given a heat of fusion and a heat of vaporization. The heat of fusion for lead is 2.04 times 10 to the 4 joules per kilogram. So 2.04. So for this bit, my HF equals 2.04 times 10 to the 4 joules per kilogram. Right there. So I have my M and my HF. I can substitute and solve for this for my second step. So my mass, 1 kilogram, my HF, 2.04 times 10 to the 4 joules per kilogram. Checking those units. Kilograms on top, kilograms on the bottom, left with joules. Okay, good, that's what I want. And 1 times anything will just be whatever that thing was. So 2.04 times 10 to the 4. If we want to write that out as an actual number to compare it with this one, so our number above would be 20400 joules. Okay, now we have this much joules, this much energy to turn my solid lead into liquid lead, and it takes this much energy to turn my solid lead to its melting temperature. So to figure out how much energy in total is needed, so how much heat in total is needed to melt this lead, I just add my two together. Okay, so my total energy will be the sum of my steps, the energy required in my steps. So step 1 energy plus step 2 energy. And then we need to, so step 5 is to find the sum of the heat in all our steps. Okay, so my total energy will be 39,585, sorry, this is lagging, joules plus 20,400 joules. And we end up getting work 59,985 joules. Now take a peek up. We're multiplying and dividing in these guys. I'm not going to make you do a lot of evil significant figure calculations. Just multiplying and dividing, we'll have 2, 3, 4, so we need to round to 2. So cut off here, take a peek over. And our total energy, so the heat needed is 60,000 joules. But I need two significant figures. That's just one significant figure. So for this question, we actually have to put our answer into scientific notation. So 6.0, there, now I have two. And then times 10 to the 1, 2, 3, 4 joules needed to melt the ice. Sorry, melt the lead, not the ice. Okay, another example. If you want, I'm not going to do it here. These notes are already long enough. We can try a 4 to 5 stepper together, but I will do that on a separate video. So we will see how much heat is lost when you have steam at 105.1 degrees Celsius turning into ice at negative 6.8 degrees Celsius. So if you want to see a 4 to 5 stepper and do that together, we will do that. Okay, and it's also a heat is lost instead of a heat is how much heat you're adding. So it'll be a negative heat. Okay, so if you want to view that, you can after this. Or you can just turn to page 325 and start on the assignment 19 to 21. Okay,